Second, R is specially developed for vector operations. That means it's able to go through an entire list of data without having to write for loops to go through it. If you've ever had to write for loops, then you know that that would be kind of disastrous having to do that with data analysis. Next, R has a fabulous community behind it. It's very easy to get help on things with R. You Google it, you're going to end up in a place where you're going to be able to find good examples of what you need. And probably most importantly, R is very capable on its own, but there are 7,000 packages, actually it's many more than that, 7,000 packages that add capabilities to R. Essentially, it can do anything. Now, when you're working with R, you actually have a choice of interfaces. That is, how do you actually do the coding and how do you get your results? R comes with its own IDE, or interactive development environment. You can do that, or if you're on a Mac or a Linux, you can actually do R through the terminal, through command line. If you've installed R, you just type R and it starts up. There's also a very popular development environment called RStudio, and that's actually the one that I use and I'll be using for all of my examples. But another new competitor is Jupyter, which is very commonly used for Python. It's what I use for examples there. It works in a browser window, even though it's locally installed. And RStudio and Jupyter, there's pluses and minuses to each one of them. I'll mention them as we get to them. But no matter what interface you use, R's command line, you are typing lines of code in order to get the commands. Some people get really scared about that, but really there's some advantages to that in terms of the replicability and really the accessibility, the transparency of your commands. So for instance, here's a short example of some commands in R. You can enter them into what's called the console, and that's just like one line at a time. That's called an interactive way. Or you can save scripts and run bits and pieces of them selectively. That makes your life a lot easier. No matter how you do it, if you're familiar with programming in other languages, then you're going to find that R is a little weird. It has an idiosyncratic model. It makes sense once you get used to it, but it is a different approach. And so it does take some adaptation if you're accustomed to programming in other languages. Now, once you do your programming and get your output, what you're going to get is graphs in a separate window. You're going to get text and numbers, numerical output in the console. And no matter what you get, you can save the output to files. So that makes it portable. You can do it in other environments. But most importantly, I like to think of this. Here's our box of chocolates where you never know what you're going to get. The beauty of R is in the packages that are available to expand its capabilities. Now, there are two sources of packages for R. One goes by the name of CRAN, and that stands for the Comprehensive R Archive Network. And that's at cran.rstudio.com. And what that does is it takes these 7,000 or so different packages that are available, and it organizes them in topics that they call task views. And for each one, if they've done their homework, you have data sets that come along with that package. You have a manual in PDF format, and you can even have vignettes where they run through examples of how to do it. Another interface is called Crantastic, and the exclamation point is part of the title. That's at crantastic.org. And what this is an alternative interface that links to CRAN. So if you find something like in Crantastic and you click on the link, it's going to open in CRAN. But the nice thing about Crantastic is it shows the popularity of packages, and it also shows how recently they were updated. And that can be a nice way of knowing that you're getting sort of the latest and greatest. Now, from this very abstract presentation, we can say a few things about R. Number one, according to many, R is the language of data science. And it's a command line interface. You're typing lines of code. So that gives it both a strength and it's a challenge for some people. But the beautiful thing is the thousands and thousands of packages of additional code and capability that are available for R that make it possible to do nearly anything in this statistical programming language. When talking about coding in data science in the languages, along with R, we need to talk about Python. Now, Python, the snakes, is a general purpose program that can do it all, and that's its beauty. If we go back to this survey of the software used by data mining experts, you see that Python's there. It's number 3 on the list. And what's significant about that is on this list, Python is the only general purpose programming language. It's the only one that can theoretically be used to develop any kind of application that you want. That gives it some special power compared to all these others, most of which are very specific to data science work. So the nice things about Python are, number one, it's general purpose. It's also really easy to use. And if you have a Macintosh or a Linux computer, Python is built into it. Also, Python has a fabulous community around it with hundreds of thousands of people involved. And also, Python has thousands of packages. Now, it actually has something like 70 or 80,000 packages, but in terms of ones that are specific to data, there are still thousands available that give it some incredible capabilities. Now, a couple of things to know about Python. First is about versions. There are 2 versions of Python that are in wide circulation. There's 2.x, so that means like 2.5, 2.6, and there's 3.x, 3.1, 3.2. Version 2 and version 3 are similar, but they're not identical. And in fact, the problem is this. There are some compatibility issues where code that runs in one does not run in the other. And consequently, most people have to choose between one or the other. And what this leads to is that many people still use 2.x. I have to admit, the examples that I use, I'm using 2.x because so many of the data science packages are developed with that in mind. Now, let me say a few things about interfaces for Python. First, Python does come with its own interactive development and learning environment. They call it idle. You can also run it from the terminal or command line interface or any IDE that you have. Now, a very common and very good choice is Jupyter. Jupyter is a browser-based framework for programming, and it was originally called IPython, and that served as its initial version. So a lot of times when people talk about IPython, what they're really talking about is Python in Jupyter, and the two are sometimes used interchangeably. One of the neat things you can do is there are 2 companies, there's Continuum and Endthought, both of which have made special distributions of Python with hundreds and hundreds of packages pre-configured to make it very easy to work with data. I personally prefer Continuum Anaconda. It's the one that I use. A lot of other people use it, but either one's going to work and it's going to get you up and running. And like I said with R, no matter what interface you use, all of them are command line. You're typing lines of code. Again, there are some tremendous strengths to that, but it can be intimidating to some people at first. In terms of the actual commands of Python, you have some examples here on the side. The important thing to remember is that it's a text interface. On the other hand, Python is familiar to millions of coders because it's very often a first programming language that people learn to do general purpose programming. And there are a lot of very simple adaptations for data that make it very powerful for data science work. So let me say something else again. Data science loves Jupyter, and Jupyter is the browser-based framework. It's a local installation, but you access it through a web browser that makes it possible to really do some excellent work in data science. There's a few reasons for this. When you're working in Jupyter, you get text output, and you can use what's called Markdown as a way of formatting documents. You can get inline graphics where the graphics just show up directly beneath the code that you did it. Also, it's really easy to organize and present and to share analyses that are done in Jupyter, which makes it a strong contender for your choices in how you do data science programming. Another one of the beautiful things about Python, like R, is that there are thousands of packages available. In Python, there's one main repository. It goes by the name PyPy, which is for the Python Package Index. Right here, it says there's over 80,000 packages, and 7,000 or 8,000 of those are for data-specific purposes. Now, some of the packages that you'll get to be very familiar with are NumPy and SciPy, which are for scientific computing in general. Matplotlib and a development of it called Seaborn are for data visualization and graphics. Pandas is the main package for doing statistical analysis. And for machine learning, almost nothing beats scikit-learn. And when I go through hands-on examples in Python, I will be using all of these as a way of demonstrating the power of the program for working with data. So, in sum, we can say a few things. Number one, Python is a very popular program, familiar to millions of people, and that makes it a good choice. Second, of all the languages we use for data science on a frequent basis, This is the only one that's general purpose, which means it can be used for a lot of things other than processing data. And it gets its power, like R does, from having thousands of contributed packages, which greatly expand its capabilities, especially in terms of doing data science work. A choice for coding in data science, one of the languages that may not come immediately to mind when they think data science, is SQL or SQL. And SQL is the language of databases. And we think, why do we want to work in SQL? Well, to paraphrase the famous bank robber Willie Sutton, who apparently explained why he robbed banks and said, because that's where the money is. The reason we would work with SQL in data science is because that's where the data is. And so let's take another look at our ranking of software among data mining professionals. And there's SQL. It's third on the list. And also of this list, it's the first database tool. Other tools in there, for instance, get much fancier and they're much newer and shinier, but SQL's been around for a while and is very, very capable. Now there's a few things to know about SQL. By the way, you'll notice I'm saying SQL, even though that stands for something. It stands for Structured Query Language. SQL is a language. It's not an application. There's not a program SQL. It's a language that can be used in different applications. Primarily, SQL is designed for what are called relational databases. And those are special ways of storing structured data that you can pull in, you can put things together, you can join them in special ways, you can get some summary statistics. And then what you usually do is you then export that data into your analytical application of choice. So the big word here is RDBMS, and that stands for Relational Database Management System. And that's where you will usually see SQL as a query language being used. In terms of relational database management systems, there are a few very common choices. In the industrial world where people have some money to spend, there's Oracle database is a very common one, and Microsoft SQL or SQL Server. In the open source world, two very common choices are MySQL. Even though we generally say SQL, when it's here, you generally say MySQL. And then another one is PostgreSQL. These are both open source free versions of the language. They're sort of dialects of each that make it possible for you to be working with databases and get your data out. The neat thing about them, no matter what you do, is that databases minimize data redundancy by using connected tables. Each table has rows and columns, and they store different levels or different of abstraction or measurement, which mean you only have to put the information in one place and then it can refer to lots of other tables. Makes it very easy to keep things organized and up to date. When you're looking at a way of working with a relational database management system, you get to choose in part between using a graphical user interface or GUI, and some of those include SQL Developer and SQL Server Management Studio, two very common choices. And there are a lot of other ones like Toad and some other choices that are graphical interfaces for working with these databases. And there are also text-based interfaces. So really any command line interface and any interactive development environment or programming tool is going to be able to do that. Now you can think of yourself being on the command deck of your ship and learn a few basic commands that are very important for working with SQL. There are just a handful of commands that can get you most of where you need to go. There is the select command where you're choosing the cases that you want to include. From says which tables are you going to be extracting them from. Where is a way of specifying conditions, and then order by, obviously, is just a way of putting it all together. This works because usually when you're in a SQL database, you're just pulling out the information. You want to select it, you want to organize it, and then what you're going to do is you're going to send the data to your program of choice for further analysis, like R or Python or whatever. So in sum, here's what we can say about SQL. Number one, as a language, it's generally associated with relational databases, which are very efficient and well-structured ways of storing data. Just a handful of basic commands can be extremely useful when working with databases. You don't have to be a super ninja expert. Really, a handful, 5, 10 commands will probably get you everything you need out of a SQL database. And then once you get the data organized, it's typically exported to some other program for analysis. When you talk about coding in any field, one of the languages or one of the groups of languages that come up most often are C, C++, and Java. Now, these are extremely powerful applications and very frequently used for sort of professional production level coding. In data science, the place where you're going to see these languages most often is in the bedrock, the absolute fundamental layer that makes the rest of data science possible. So for instance, C and C++. C is from the 60s, C++ is from the 80s, and they have extraordinarily wide usage. And their major advantage is that they're really, really fast. In fact, C is usually used as the benchmark for how fast is a language. They're also very, very stable, which makes them really well suited to production level code and, for instance, server use. What's really neat is that in certain situations, if time is really important, if speed's important, then you can actually use C code in R or other statistical languages. Next is Java. Java is based on C++. Its major contribution was the WARA, or write once, run anywhere. The idea that you're going to be able to develop code that is portable to different machines and different environments. And because of that, Java is actually the most popular computer programming language overall against all tech situations. And the place where you would use these in data science is, like I said, when time is of the essence, when something has to be fast, it has to get the job accomplished quickly, and it has to not break, then these are the ones that you're probably going to use. The people who are going to use it are primarily going to be engineers. So the engineers and the developers, the software developers who deal with the inner workings of the algorithms in data science, or the back end of data science, the servers and the mainframes and the entire structure that makes analysis possible. In terms of analysts, people who are actually analyzing the data typically don't do hands-on work with the foundational elements. They don't usually touch C or C++. More the work is on the front end or closer to the high-level languages like R or Python. In sum, C, C++, and Java form a foundational bedrock and the back end of data and data science. And they do this because they're very fast and they are very reliable. On the other hand, given their nature, that work is typically reserved for the engineers who are working with the equipment that runs in the back that makes the rest of the analysis possible. I want to finish our extremely brief discussion of coding in data sciences and the languages that can be used by mentioning one other that's called Bash. And Bash really is a great example of old tools that have survived and are still being used actively and productively with new data. You can think of it this way. It's almost like typing on your typewriter. You're working at the command line. You're typing out code through a command line interface, or CLI. Now, this method of interacting with computers practically goes back to the typewriter phase because it predates monitors. So before you even had a monitor, you would type in the code and it would print it out on a piece of paper. And the important thing to know about the command line is it's simply a method of interacting. It's not a language because lots of different languages can run at the command line. So for instance, it's important to talk about the concept of a shell. Now in computer science, a shell is a language or something that wraps around the computer. It's a shell around the language that is the interaction level for the user to get things done at the lower levels that aren't really human friendly. On Mac computers and Linux, the most common is Bash, which is short for Born Again Shell. On Windows computers, the most common version is PowerShell. But whatever you do, there actually are a lot of choices. There's the Bourne shell, there's the C shell, which is why I have a C shell right here. The Z shell, there's Fish for a friendly interactive shell, and a whole bunch of other choices. But Bash is the most common on Mac and Linux, and PowerShell is the most common on Windows as a method of interacting with the computer at the command line level. Now there's a few things you need to know about this. First, you have a prompt of some kind. In Bash, it's a $sign, and that just means type your command here. Then the other thing is you type one line at a time. It's actually amazing how much you can get done with what's called a one-liner program by sort of piping things together so one feeds into the other. You can run more complex commands if you use a script. And so you call a text document that has a bunch of things in it, and you can get much more elaborate analyses done. Now we have our tools here. In Bash, we talk about utilities. And what these are specific programs that accomplish specific tools. Bash really thrives on do one thing and do it very well. There are two general categories of utilities for Bash. Number one is the built-ins. These are the ones that come installed with it, and so you're able to use them at any time by simply calling in their name. Some of the most common ones are cat, which is for catenate, and that's to put information together. There's awk, which is its own interpreted programming language, but it's often used for text processing from the command line. By the way, the name awk comes from the initials of the people who created it. Then there's grep, which is for global search with a regular expression and print. It's a way of searching for information. And then there's sed, which stands for stream editor. And its main use is to transform text. You can do an enormous amount with just these four utilities. A few more are head and tail that display the first or last 10 lines of a document. Sort and unique, which sort and count the number of unique answers in a document. WC, which is for word count. And printf, which formats the output that you get in your console. And while you can get a huge amount of work done with just this small number of built-in utilities, there are also a wide range of installables or other command line utilities that you can add to Bash or to whatever program you're using. So for instance, some really good ones that have been recently developed are JQ, which is for pulling in JSON or JavaScript object notation data from the web. And then there's JSON to CSV, which is a way of converting JSON to CSV format, which is what a lot of statistical programs are going to be happier with. There's Rio, which allows you to run a wide range of commands from the statistical programming language R in the command line as part of Bash. And then there's BigMLer. And this is a command line tool that allows you to access BigML's machine learning servers through the command line. Normally you do it through a web browser and it accesses their servers remote. It's an amazingly useful program, but to be able to just pull it up when you're in the command line is an enormous benefit. What's interesting is that even though you have all these opportunities, all these different utilities, you can do amazing things, and that there still is active development of utilities for the command line. So let's say this, in sum, despite being in one sense as old as the dinosaurs, the command line survives because it is extremely well evolved and well suited to its purpose of working with data. The utilities, both the built-in and the installables, are fast and they are easy. And generally they do one thing and they do it very, very well. And then surprisingly, there is an enormous amount of very active development of command line utilities for these purposes, especially with data science. One critical task when you're coding in data science is to be able to find the things that you're looking for. And regex, which is short for regular expressions, is a wonderful way to do that. You can think of it as the supercharged method for finding needles in haystacks. Now, regex tends to look a little cryptic. So for instance, here's an example of something that's designed to determine whether something is a valid email address. And it specifies what can go in the beginning. You have the @ sign in the middle, then you've got a certain number of numbers and letters, and then you have to have a dot something at the end. And so this is a special kind of code for indicating what can go where. Now, regular expressions or regex are really a form of pattern matching in text. And it's a way of specifying exactly what needs to be where, what can vary, and how much it can vary. And you can write both specific patterns, say I only want a one letter variation here, or very general, like the email validator that I showed you. And the idea here is you can write this search pattern, your little wildcard thing. You can find the data, and then once you identify those cases, then you can export them into another program for analysis. So here's a short example of how it can work. What I've done is I've taken some text documents. They're actually the text to Emma and to Pygmalion, two books I got off of Project Gutenberg. And this is the command grep::l.ve space *.txt. So what I'm looking for are lines in either of these books that start with L. Then they have one character, it can be whatever, and then that's followed by VE. And then the .txt means search for all of the text files in that particular folder. And what it found is lines that began with love and lived and lovely and so on. Now, in terms of the actual nuts and bolts of regular expressions, there are some certain elements. There are literals, and those are things that mean exactly what they are. You type the letter L, you're looking for the letter L. There are also meta characters, which specify, for instance, things needs to go here. They're characters, but they actually really code that give representations. There are also escape sequences, which are something that you use to say, well, normally this character is used as a variable, but I actually want to really look for a period as opposed to a placeholder. Then you have the entire search expression that you create, and then you have the target string, the thing that it's searching through. So let me give a few very short examples. This is the caret. It's sometimes called a hat, or in French, a circonflexe. And what that means is you're looking for something that's at the beginning of the text that you're searching. So for example, you can have caret and capital M. That means you need something that begins with a capital M. So for instance, the word Mac, true, it will find that. But if you have iMac, there's a capital M, but it's not the first thing. So that'll be false. It won't find that. The $sign means you're looking for something that is at the end of the string. So for example, ing and then $sign, that'll find the word fling because it ends with ing, but it won't find the word flings because it actually ends with an S. And then the dot, the period, simply means we're looking for one letter, and it can be anything. So for example, you can write AT period, and that will find data because it has an A, a T, and then one letter after it. But it won't find flat because flat doesn't have anything after the AT. And so these are extremely simple examples of how it can work. Obviously, it gets more complicated, and the real power is when you start combining these bits and elements. Now, one interesting thing about this is you can actually treat this as a game. I love this website. It's called regex golf, and it's at regex.alf.nu. And what it does is it brings up lists of words, 2 columns, and your job is to write a regular expression in the top that matches all the words on the left column and none of the words on the right, and that uses the fewest characters possible. And you get a score. And it's a great way of learning how to do regular expressions and learning how to search in a way that's going to get you the data that you need for your projects. So, in sum, regex or regular expressions help you find the right data for your project. They're very powerful and they're very flexible. Now, on the other hand, they are cryptic, at least when you first look at them. But at the same time, it's like a puzzle, and it can be a lot of fun if you practice it and you see how you can find what you need. I want to thank you for joining me in coding and data science, and we'll wrap up this course by talking about some of the specific next steps that you can take for working in data science. The idea here is that you want to get some tools and you want to start working with those tools. Now, please keep in mind something that I've said at another time. Data tools and data science are related, they're important, but don't make the mistake of thinking that if you know the tools that you have done the same thing as actually conducted data science. That's not true. People sometimes get a little enthusiastic and they get a little carried away. What you need to remember is the relationship really is this. Data tools are an important part of data science, but data science itself is much bigger than just the tools. Now, speaking of tools, remember there's a few kinds that you can use and that you might want to get some experience with these. Number one, in terms of apps or just specific built applications, Excel and Tableau are really fundamental for both getting the data from clients or doing some basic data browsing. And Tableau is really wonderful for interactive data visualization. I strongly recommend that you get very comfortable with both of those. In terms of code, it's a good idea to learn either R or Python, or ideally to learn both, because you can use them hand in hand. In terms of utilities, it's a great idea to learn how to work with